This is video 31 in the series on reinforced concrete slabs, but it will deal with the design of columns. We will now have a word on the slenderness and effective length of a column. First, we start with the effective length. It is well known that when you have a column with two hinged on both sides, then the effective length is equal to the length in reality. And when it is clamped or fixed at the bottom and free on top, then it's 2L, the effective length. You have now different situations where you can calculate the effective length. Slenderness. The slenderness is defined as the effective length divided by y, and y is the radius of gyration of the uncracked cross section without reinforcement. So the radius of gyration just of the concrete only, uncracked, is the square root of the E divided by the surface of the divided by the cross section of the element in consideration. Just to give you a few ideas, what is the value of slenderness? What does that mean? Then you will see in this table the slenderness of a column with a square cross section, and you see that, for instance, the slenderness of 50 means a column of a size 200 by 200 and 3 meters high. That's a slenderness of 50. A slenderness of 40 is a column of 300 by 300 and 3.5 meters high. So now you have an idea what is slenderness, what it does mean, the value of those different examples. For a rectangular cross section, the slenderness is of course L0 divided by the radius of gyration, and we obtain square root of 12 L0 divided by H. H is here the size of the cross section. And for a circular cross section, we can do the same exercise, and then we see it's 4 L0 divided by the diameter of the cross section. So slenderness, in both cases, if you compare it, is proportional to the effective length, L0, and inverse proportional to a dimension of the cross section, H or D, in the direction of bending. Don't forget that. It's the dimension of the cross section in the direction of the bending. Now, a column with a square or a circular cross section, and you can choose. And now we suppose that we have the same buckling length, and or we have the same effective length, and cross-sectional area is the same. Two columns identical to each other, same quality grade, and so on. Which column do you prefer now? You have a square column with a size A, then and the cross section is equal to that of the circle, then it means that A squared must be equal to PD squared over 4, or D is 2A divided by square root of pi. Now we take the square cross section, we calculate y, and the cross section, we calculate the radius of gyration, and we obtain A divided by the square root of 12. We calculate the slenderness lambda 0, and we see that lambda 0 is 3.46 L0 divided by A. For the circle cross section, E is PD to the power 4 divided by 64. The cross section is PD squared over 4, and the radius of gyration is D over 4. Then lambda equals L0 over E, and when we substitute all the different values in it, we obtain, in fact, and we have to substitute D, which is equal to 2A over square root of pi, because of the surface, because of the cross section is equal, we obtain 3.54. So this means that the slenderness of the circle cross-section is higher than the slenderness of the square cross-section. So when you have the choice, use the square cross-section, which is better. It has a higher loading capacity with the same circumstances as the circular cross-section. Buckling is failure due to instability of an element or structure under centric axial pressure and without any transverse loads. So it's just an element with a centric axial pressure, and this element fails, and that we call buckling. Buckling load is the load where buckling occurs. For isolated elastic elements, it is equal to the Euler load. Second order effects or buckling may be ignored if the slenderness is below a certain value lambda limit. And lambda limit is 20 ABC divided by the square root of n. N is a load rate, and it is the axial force in ULSP divided by the cross-section of the concrete multiplied by its stress, by its maximum compressive stress. So n is 1, that's the largest value, and that's why we call it the load rate. A is a factor taking into account the shrinkage or the effective creep. And when the effective creep is not known during the lifetime or during the period that you consider this column, then you can take it as 0.7. B is dependent on the reinforcement, the mechanical reinforcement ratio. And C is dependent on the moment distribution. And the moment distribution is MO1 on top divided by MO2 on the bottom, and NO2 is the largest in absolute value. The effective creep coefficient is in fact the creep coefficient at infinity multiplied by a ratio of two bending moments. The one is in SLSQ divided by a bending moment in ULS. This is a formula making a combination of LSQ and ULS, so take care of it. It's just a definition of effective creep coefficient. The effect of creep may be ignored when this condition is fulfilled, all of them. So the actual creep coefficient must be smaller than 2, which is often the case. Slenderness smaller than 0.7, but than 75, and the eccentricity of the normal force must be larger than h. Let's take the most common case. Then A is 0.7, B is 1.1, and C is 0.7. That's the most common case. And then the formula of lambda limit is equal to the formula here. It's 10.78 divided by the square root of the load rate. You can make a little graph of it. The load rate is mentioned on the x-axis, and the lambda limit, the limit value of the slenderness, is marked on the y-axis. And then you see that the load rate, when the load rate is half of the capacity of the cross-section, that lambda limit is only 15. So it means that almost in every column you have to take slenderness into account, because 15 is very small as a slenderness ratio. And this is only at 50% load. When lambda is bigger than lambda limit, then we have to take buckling into account. It means that lambda limit in the most general case is equal to this formula. N was this. And then at n equals 0.5, half, then the lambda limit is 15, like we just said in the previous slide. The consequence is, of course, that you have to base your pre-design on slenderness and less on strength, because strength will always be okay, but your slenderness will be exceeded. So base your pre-design on slenderness. And we will give an example of the square cross-section at a load percentage of 50%. Then lambda must be smaller than 15, or you can express lambda for a square cross-section with side A, or A must be bigger than 0.20 through L0. This means that the size of your column must be bigger than 1/4 of the total length of the column. This is a huge column. So you will see that if you want to design a column without taking into account slenderness, you will end up with very, very large columns, which is not economical. Take, for instance, a very, very low design compressive strength of for instance, 0.1 megapascal, which is quite ridiculous. But you take a very low design compressive strength of 0.1 megapascal. You calculate the load rate, and load rate is 0.006. Then you calculate the limit value for slenderness, and you will have 140. So this gives you a very good idea that you will try not to exceed a slenderness of 140. That's where the figure is coming from, because it only it allows you only with a total compressive strength or compressive stress of 0.1 megapascal. So you will not utilize the column very well. So never exceed a slenderness of 140. So keep lambda smaller than 140 means that L0 over I will be smaller than 140. And for a square column, it means that the slenderness of the effective length, must be smaller than 40 times the size. So the maximum length of a hinged column is 40 times the side, and for a model column, it's of course only 20 times the side of the cross section. This is a huge implication because now we can just have a small table. That means that a column with a cross section of 200 by 200 millimeters can only have a maximum height of a maximum length, effective length of 8 meters. A column of 250 by 250 is 10 meters, and by 300 of 300, the maximum length is 12 meters. Never exceed this because this is very dangerous. An estimate of a column dimension, a square column dimension, without the need of checking second order bending moments, then we know lambda is lambda limit. We've seen this. Lambda limit is equals to this value and lambda is equals to that value. It means that A must be equal to this formula. And the load rate is equal to the normal force divided by this value, and AC is A squared, and FCD, let's suppose it's a concrete grade 30, so it's 0.85 times 30 divided by the material coefficient 1.5, and it is 17 megapascal. So this means that from this is the condition for slenderness, and this is the condition for strength. We have 2 times a form of A, and when you combine those two, then you see that the size of the column must be equal to 0.28 L0 to the power of 0.5 and the normal force to the power of 0.25. So this is, if you now you can take a typical load of a column in a building is 100 tons or 1,000 kilonewton, and a typical length of a column is between 3 and 5 meters. So you see that for 3 meters, your column size that you need is 485, and the load ratio of the load rate is 0.25. For 4 meters, you need 560 millimeters, and for 5 meters you need 626 millimeters and only a load rate of 0.15. This formula gives you an idea of a first estimate of the size of column you need on the condition that you will not take second order bending into account. Immediately you can see from the table this is not very economically. We will not do that. When you have only 3 meters as a length between two levels of a building, you will not make columns with this size. This is too big. So you have to take into account slenderness. And we do that by just adopting this formula by dividing by a square root of beta, and beta is the number of times that lambda limit is superseded. So this is a choice of the designer. You can choose that. And commonly we will use 4. We will exceed lambda limit 4 times. So you have to take slenderness into consideration, but then you will have an economic design of the column. And this is a formula now that you can use for an estimate for a pre-design, that the side of the length of the cross section of the square of a column is equal to 0.8 times the square root of the buckling length in millimeters. Sorry, I forgot to tell that. The dimensions are millimeter, millimeter, and kilonewton. And NAD is a normal acting force in ultimate limit state permanent and is in kilonewton. And this formula implies that we have used a factor of 4. So it means that the slenderness is 4 times the limit value of the slenderness. This is a very easy formula to estimate in a very quick way the needed dimension of a column.